Here's a really nice theorem. If sigma of n, that is, you add up all the divisors of n, that's what sigma of n is. If that's odd, sigma of n is odd, that is, the sum of all the positive divisors of n is odd, if and only if n is a perfect square, or n is twice a perfect square. Okay, so let us prove this. If you like seeing mathematical proofs like I'm about to write for this theorem, you should seriously consider subscribing to my channel, as that's what we do here. Okay. Let n equal p1 to the k1 times p2 to the k2 all the way up to p sub r to the k sub r, where sigma of n is odd. Now, sigma of n is equal to 1 plus p sub 1 plus p sub 1 squared all the way up to plus p sub 1 k to the 1 times, same game with p sub 2. I proved this in a prior video. 1 plus p sub 2 plus p sub 2 squared all the way up to p sub 2 raised to the k sub 2. And we keep multiplying all the way until we get to the p sub r prime. 1 plus p sub r plus p sub r squared all the way up to p sub r to the k sub r. And, okay, since q sub n is odd, none of these can be even. No 1 plus p sub I plus p sub I squared up to p sub I to the k sub I is even. Okay, none of these are even. That is, they're all odd. That is 1 plus p sub I plus p sub I squared all the way up to p sub I k sub i's are all odd. Well, that implies that k sub I is even for all I equal 1, 2 up to r. Okay, that is, all of these exponents are even. That implies n is a perfect square. Okay, n is a perfect square because if n is equal to 7 squared times 5 squared times 3 to the 6 times 11 to the 8, this is 7 times 5 times 3 cubed times 11 to the 4th all squared. Because you get 7 squared, there it is. You get 5 squared, there it is. You get 3 cubed squared, which is 3 to the 6, there it is. And then you get 11 to the 4th squared, which is 11 to the 8th. And this is a perfect square. But question is, can there be another way of getting a perfect square? That surely is one option. Well, I didn't mean to say that. Is there another way for sigma of n to be odd? there's another way for sigma of n to be odd. Clearly, so yes, it is a perfect square. Yes. Okay, the question is, so let me just say something up here. And 2 is not any of the p sub i's. Okay, so we do have a perfect square. Now I'm going to make a claim. 2 to the k sub 0. Sigma to k sub 0. This is going to be odd if k sub 0 is at least 1. Okay. To see this is simple. What can possibly be the divisors of 2 to a power? Note that divisors of 2 to the k 0 are 1, 2 to the 1, 2 to the 2, 2 to the 3, all the way up to 2 to the k sub 0. These that I just underlined are all even. So when you add them up, you're going to get even. And that's what sigma does. It adds up all the prime factors. It adds up all the divisors. But then you add 1. This implies that sigma of 2 to the k 0 is 1 plus 2 plus 2 squared plus 2 cubed, all the way up to 2 to the k 0. This is even. You add 1 to it, you get odd. Okay. So what happens is they don't all have to be even. Sorry. So not all the powers have to be even. You can have odd powers of 2. In other words, sigma of 8. The only numbers that go into 8 evenly are 1, 2, 2 squared, and 2 cubed. You add those, you get even. 1 more is odd. So that's another way of getting a perfect square. Of course, this power, k sub 0, would have to be even. Because, for example, 2 is not a power, is not a perfect square. Nor is 8 a perfect square. Okay, so let's incorporate this. So let n equal to 2 to the k sub 0 times p to the p1 to the k1 times p2 to the k2 all the way up to p sub r to the k sub r, where k sub I is even for I going from 1 to r. That is not 0. So what happened is, we know this is a perfect square. You know what? Let's even have okay, so let's scratch this. There are 2 cases. Case 1, k sub 0 is odd, and case 2 where it will be even. K0 odd implies that k sub 0 is 2n plus 1. Okay. So now you have 2 to the n plus 1 times p1 to the k1 all the way down to p sub r to the k sub r. And where k sub I is even and n is m is any integer. Okay, so what you have here is the following. So that's n. So n is equal to 2 times, that should say 2m, excuse me. 2 is being raised to an odd power. So that's 2 times 2 to the m, p1 to an even power, all the way down to p r to their kr. And once again I have a mistake. This should be 2m. But that's 2 times 2 to the m squared times p1 to an even number times p2 to an even number all the way down to k sub r to an even number. Now the thing is that I just wrote n as 2 times a perfect square. Let us see if it is odd. Sigma of n, I'm going to come to this one. Sigma of n is sigma of 2 to the 2m plus 1 times p1 to the k1 all the way up to pr to the k sub r. Now, think of those as 2 different numbers. These numbers are relatively prime. This is equal to sigma of 2 to the 2m plus 1 times sigma of the rest. Sigma of p1 to the k1 all the way up to pr to the kr, where I'm going to say that the GCD of 2 to the 2m plus 1 and p1 to the k1 up to pr to the k sub r is 1. And if that's true, then it's multiplicative. I could separate them. But as I proved above, this is odd. And we proved somewhere earlier that that's a perfect square. Okay, and sigma of this is odd. Sigma of n is odd if all their powers are even. If all the powers are even, which I'm saying they are, okay, we already said that they're even, then this is odd. And the product is odd. That is, sigma of n is odd. And sigma of n is 2 times a perfect square. So I showed that if 2 was not involved, then the only way you get odd is if each of these powers are even, which makes it a perfect square. I did a claim where I said sigma of 2 to any power is odd, including 1. If k to the 0 was 1, then this will be sigma. Actually, it doesn't even, it can be 0. Sigma of 1 is 1, an odd number. But let's not get carried away. Okay, now, case 2. What if k sub 0 is even? Case 2. k sub 0 is even. Well, that implies that k sub 0 is 2 sub m. And what happens here is you have 2 to the 2m times p1 to the k1 all the way up to pr to the kr. Remember, all of those powers are even, and even the power of 2 to the m is even. This is equal to a perfect square, since all the powers of, I was going to say primes, but 2 to the m is not prime. It could be if m is 1, since all the powers are even. Okay, so if k sub 0 is even, now what I have is, I don't have 2 times a perfect square. I just have a perfect square. When k sub 0 is odd, I have 2 times a perfect square. All the k sub i's are even, and the power of 2 to the m is even. So here I get 2 times a perfect square. So let's state that. So n is equal to twice a perfect square. And we're assuming n, sigma of n, is odd. Okay, so n can be twice a perfect square. And that's because sigma of only 2 is odd. I meant to say, yeah, is odd. Unless you're a perfect square. Sigma of 5 is 6. But sigma of 4, a perfect square, is odd. Sigma of twice a perfect square is odd. Any other number, forget about it. Okay, so do have one little problem. I should have said that we're going in the forward direction. Now we're gonna go in the reverse direction. If n is a perfect square, I have to show that sigma of n is odd. If n is twice a perfect square, I have to show sigma of n is odd. So there's 2 parts in this one. So we're going in the other direction, and we have part 1. Show that if n is a perfect square, then sigma of n is odd. Okay, proof. Let me not say proof. I already wrote proof at the top. Okay, so this is what we need to establish. Okay, so let n equal to p1 to the 2 k1, p2 to the 2 k sub 2, all the way up to p sub r to the 2 k sub r. And this is equal to p1 to the k1 times all the way up to pr to the k sub r squared. So n equal that, which equals this, is a perfect square. Now I need to show that sigma of it is odd. So I'm going to use this representative of n. So sigma of n is equal to 1 plus p1 plus p1 squared all the way up to plus p sub 1 to the 2k1 times 1 plus p sub 2 plus p sub 2 squared all the way up to p sub 2 to the k sub 2 power, and so on up to p sub r. 1 plus p sub r plus p sub r squared all the way up to p sub r to the 2 times k sub r. If these powers, since this power is even, this is odd. Oh, that's also even. Odd. In fact, all the powers are even. So the product is odd. So note that for each I, 1 plus p1, 1 plus p sub I, plus p sub I squared, all the way up to p sub I to the 2 sub ki is odd. So sigma of n, being a product of odd factors, being a product of odd factors, is odd. Let's just clearly state it. That is, sigma of n is odd. Now, what did I start off with? Let n be a perfect square. Sigma of n is odd. Okay. Now let's go to the other. Let's do. Did I call them case part 1? Part 2. Part 2. Let n equal 2 times a perfect square. Let it equals 2 times a perfect square. Let n equal 2 times. Now, we may have some more factors of the base 2. We have 2 raised to the 2k times p1 raised to the 2k sub 1 all the way down to 2 times, p sub r to the k sub r. This would equal to 2 times 2 times p1 times p2 up to p sub r squared. This here is a perfect square, and it is 2 times it. It is 2 times a perfect square. Let's get rid of all of this writing. This is equal to this 2 times a perfect square. Okay. So sigma of n, now it's okay for that to be 0. 2 times 0 is 0. So sigma of n, alright, let me just state it slightly different. Then n is equal to 2 to the 2k plus 1, I distribute, times p1 to the 2k1 all the way up to PR to the 2k sub r. So sigma of n is equal to 2 to the k plus 1. Now, I don't even want to put these parentheses. I don't need them. Let's see if I can even move this a little closer. Nope. Okay. Times P1, excuse me, times this, all the way up to P sub r, this. Now, oops, it equals sigma of that. But this equals sigma of 2 to the k plus 1 times sigma of everything else. Now, why can't I separate it? Well, first of all, that's one number. You multiply it, you get one number. You raise this 2 to a certain power, at least 1, you'll get a number. The reason we are allowed to do it in this case is because the GCD of 2 to the k plus 1 and the rest, they have no common factors other than 1. They have no common factors, no common divisors. So I can do that. Now, I did a lemma. I said that 2 to the k plus 1 is odd times, we proved earlier that a perfect square, sigma of a perfect square is odd. Odd times odd is odd. So even if n is 2 times the perfect square, let n be 2 times a perfect square. Then sigma of n equals this, which equals this, which equals an odd times of odd, which is odd. Sigma of n is odd. I proved it forwards and backwards, and that completes this proof. If you like seeing mathematical proofs like this, you should seriously consider subscribing to my channel. Click the like button. Leave a comment. Like reading your comments. See you guys in the next video. Don't forget, watch and learn.